Hello students, in this video lecture I'm going to discuss part 2 of equivalent conditions related to order isomorphism for finite PO sets. Now we have already discussed the first part of equivalent conditions related to order isomorphism for finite PO sets in my earlier video. This is in continuation with that. In my earlier video I had discussed result 1, and in result 1 there were two equivalent conditions that we had discussed related to order isomorphism, and one more condition was there. So those two equivalent conditions were discussed in the first part of this video. Now coming to the second part of the video, which discusses additional equivalent conditions related to order isomorphism for finite PO sets. Now let me start with the result that I intend to discuss in this video. So this is result 2, and let me state this result first. So I'm stating this result. Let psi mapping from P to Q be a bijection where P and Q are finite PO sets, then the following conditions are equivalent. Number 1, psi is an order isomorphism. Number 2, the condition 2 is that X is strictly related to Y in P if and only if their images psi X and psi Y are related in this way, that is psi X is strictly related to psi Y in Q. And the third condition, if X is covered by Y, X covered by Y in P, X is covered by Y in P if and only if psi X, which is the image of X, is covered by psi Y, which is the image of Y in Q. So this is the statement of the result. Let me just explain to you what this result is all about, and then of course we'll come to the proof of this result. Now in this result, what we have is that psi is given to be a mapping which is a 1-1 onto mapping, because it's a bijection, so it's a 1-1 onto mapping from P and Q, where P and Q are given to be PO sets and both of them are finite. Then we have three conditions in the result which we have to prove that they are equivalent. And the first condition is that psi is an order isomorphism. The second condition is that if X and Y are related in this way, that is X is strictly related to Y in P, then this implies and is implied by. If and only if means this condition, this first condition implies the second, and also if the second condition is given to you, then the second condition implies the first condition. So X strictly related to Y in P implies and is implied by that their images psi X and psi Y are related in the same way, which means that psi X, which is the image of X, is strictly related to psi Y, which is the image of Y in Q. And we can see that this is the pictorially, this is the picture. You have there are two PO sets P and Q, which are also given to be finite, and X and Y are two elements which are taken in P. Then correspondingly the images of X and Y will be psi X and psi Y. And the second condition says that if X is strictly related to Y in P, which means X and Y are elements of P, and X is related to Y in P, but X is not equal to Y in P. Strictly related means that X and Y are related, but X and Y are distinct, they are not equal. So if X is strictly related to Y in P, then this implies that their images which are falling in the set Q, which is psi X and psi Y, they also behave in the same way, which means that psi X and psi Y will also be related to each other and they will be distinct. That is, psi X will not be equal to psi Y and they'll be related. So this is the, and this condition is if and only if, which means that if the first condition is given to you, then the second one holds, and if the second one holds, then the first one holds. So this condition is implies and is implied by. So this is the second condition. Third condition, if X and Y are elements of P again, and if X is covered by Y, then this happens. This implies and is implied by that their images psi X and psi Y also behave in the same way, which means that psi X is covered by psi Y in Q. So psi X and psi Y, of course, they are falling in the set Q. They are present in the set Q, and psi X is covered by psi Y in Q. So these three conditions, the theorem says, are equivalent, provided we are given that psi is a bijection, which means it's a 1-1 onto map, and the other condition is on the sets P and Q, which means both of them are PO sets and they are finite. And we have to show that condition 1, condition 2, and condition 3 are equivalent. Saying that they are equivalent means that if condition 1 is given, then this implies and is implied by condition 2. And if condition 2 is given, then this implies and is implied by condition 3. In fact, this means that if any one of them is given, if any one of the three is given, then the other one the other two are implied. This is what we have to show. So now, and again, as far as the definition of covering relation is concerned, I have already explained what do you mean by saying that an element is covered by another element in a PO set. In my earlier videos, I have already done that, but just for the sake of this video, let me recall the definition of covering relation once again. If you are in a PO set P and if X and Y are two elements in P, then you say that X is covered by Y. This is the notation that you use. X is said to be covered by Y if two conditions happen. The first is that X should be related to Y and X should not be equal to Y, which means that X should be strictly less than Y. This is the first thing that should happen. And secondly, if there is some Z, if there is some Z which is lying between X and Y like this, that is X is less than equal to Z is less than Y, which means X is related to Z. Not strictly, X is related to Z, less than equal to Z, and Z is less than Y, then this always implies, if this always implies that X is equal to Z, if these two conditions hold, which means that X is strictly related to Y, and if there is a Z between X and Y, which is like this, X less than equal to Z is less than Y, then this will always imply X is equal to Z. So if there is any Z in between X and Y, then that Z will be equal to X. So although I've explained this in details in my earlier videos when we were discussing covering relation, but just because we need this concept of covering relation for this particular result also. So this definition I have just recalled. And one thing more, an equivalent way of saying that X is covered by Y in P is that X is strictly related to Y. X is strictly related to Y, and there does not exist any Z in P such that X is less than Z is less than Y. So which means that if X has to be covered by Y, or if Y covers X, this is an equivalent way of saying the same thing. So if X has to be covered by Y, or if Y covers X, then there should not be any Z belonging to P which can lie between X and Y. There should be no element of P between X and Y. So that was the definition of covering a relation. Now coming back to the proof of result 2. Now, as I said, we have to show that condition 1, condition 2 and condition 3 are proved to be equivalent, which means that if any one of them is given, then the other two will automatically hold. This is what we have to show. So as far as this is concerned, this part, which means that 1 implies 2 and 2 implies 1, this has been already shown in the first part of this video, which discusses part 1 of equivalent conditions related to order isomorphism for finite PO sets. So this part has already been shown. It has been shown already that 1 implies and is implied by 2 in the first video. So this part can be had from that video. This can be combined, that particular proof which I have given in the first part of this video can be combined with this proof to get the complete proof of result 2. So this part can be seen from that particular video. Now coming to the second part of this video, in which we show that the condition 2 implies condition 3 and condition 3 implies condition 2, which means that I'm going to show that the condition 2 implies and is implied by condition 3. So this is what I'm going to show in this particular video. So we show that the condition 2 implies and is implied by condition 3, which means that the first thing that I show is that the condition 2 implies condition 3, which means that I'll be assuming condition 2 to be true, and I'll be showing that condition 3 is also true. And then again, once we are done with that, then I'll show the opposite, which means that that will be given condition 3 and we will show that condition 2 holds. So this will be so actually this particular second part is actually has two subparts. In the first subpart, we'll be showing that 2 implies 3, condition 2 implies condition 3, and in the second subpart, we are going to show that condition 3 implies condition 2. So when both these things are done, then this would imply that condition 2 implies and is implied by condition 3. So let me start with the first subpart of the second part, in which I'm going to show that condition 2 implies and is implied by condition 3, and I'm going to show firstly that condition 2 implies condition 3. So let condition 2 hold. Uh, this is the first thing that we have to assume. So now what is condition 2? Condition 2 is that if x is strictly related to y in P, this implies and is implied by, if and only if means this implies and is implied by that psi x and psi y are related in the same way, which means that the image of x psi x is strictly related to the image of y psi y in Q. So so let me suppose that, and what is that we have to show? You have to show condition 3. And what is condition 3? Condition 3 is this one, that if x is covered by y in P, then this implies and is implied by that their images behave in the same way, which means that the image of x is covered by the image of y in Q. So let me suppose this part, and then I will show this part. So let me suppose that x is covered by y in P, and then I will show that psi x is covered by psi y in Q. So coming to the proof back again. So I'll suppose that x is covered by y in P. Now we have to show that psi x is covered by psi y in Q. Now by definition of covering relation, which I just recalled, because x is covered by y, you have that x is strictly related to y in P. There are two things which hold. First is x is strictly related to y in P, which means that x is related to y in P, but x and y are distinct. And if there is any z belonging to P such that z lies between x and y in this way, which means x is less than equal to z is less than y, then this implies that x is equal to z. So these two things, this was condition 2, which we were saying that it holds for the time being, and we have to show condition 3. So this we have marked as 1, and this particular expression that we have got, this because x is covered by y, this I'm marking as 2. Now by 1, psi x is strictly related to psi y in Q. By this part, psi x is strictly related to psi y in Q. So let there be some, suppose there is some z1 belonging to Q such that z1 lies between psi x and psi y. So z1 is like this, that psi x is less than equal to z1 is less than psi y. I've marked this as 3. Then as psi mapping from P to Q is onto, because this is given, psi is given to be a bijection, and a bijection is a 1-1 onto map. This means that now because z1 is an element lying between psi x and psi y, this is the case. This is your P, this is your Q, and z1 is over here, and it lies between psi x and psi y. So now because this map psi is an onto map, this means that there should be an element z over here such that psi of z is equal to z1, because psi is onto. This is the definition of an onto map. So because psi is onto, therefore for z1 belonging to Q, we must be able to find some z belonging to P such that psi z is equal to z1. So I've marked this as 4. So we have 3 things, 1, 2, 3, this relation, and the 4th relation which we have got now, which is psi z is equal to z1. Now taking together 3 and 4, now 3 says that psi x is less than equal to z1 is less than psi y, and 4 says that the value of z1 is psi z. So putting the value of z1 in 3 over here, we have that psi x is less than equal to psi z is less than psi y. Just putting the value of z1 as psi z over here, and this would imply in view of this would actually imply this. This is what I have written. Let me just erase this statement again, because I have already written this. So using 3 and 4 together, we have that psi x is less than equal to psi z is less than psi y. We have just put, what we have done is we have just put the value of z1 over here, and this implies that x is less than equal to z is less than y in view of 1. Why? Because 1 says, because the statement 1, this statement which I have numbered as 1, this statement says that whenever you have the images are strictly related, then the element, whenever the images are strictly related in Q, then the elements are also strictly related in P, because the result holds this way also. So now here you have that psi x is less than equal to psi z is less than psi y, and this I'm saying implies x is less than equal to z is less than y, because whenever the elements whenever the images are strictly related, here there is a less than sign, here there is a less than sign, and then the elements are also strictly related. So whenever psi x is strictly less than psi z is strictly less than psi y, then this implies x is strictly less than z is strictly less than y. But so for strict, this relation definitely holds in view of 1, but here you have equality sign is also there. So how whenever there is a equality sign over here, which means that whenever psi x is equal to psi z, this would definitely imply x is equal to z. Why? Because you have psi is given to be a 1-1 function, because psi originally was given to be a bijection. So because psi is a bijection, so whenever the images are equal, the elements are equal. So because of this particular fact that psi is a bijection, the equality also is holding over here. So whenever there is a less than sign over here, then there is a less than, whenever there is a equal to sign, less than equal to sign over here, there is a less than equal to sign over here. Whenever there is equality over here, then there is equality over here, and whenever there is strict sign over here, then there is a strict sign over here. So so this is the reason that we are including less than equal to over here. So so 3 and 4 together give that psi x less than equal to psi z is strictly less than psi y, implies x is less than equal to z is less than y. This is in view of 1. Firstly, the strict part is in view of 1, and the equal to sign in both the cases, that psi x is equal to psi z implies x is equal to z. This part comes, the equality part comes because of the reason that psi is a bijection. So it is a 1-1 map. Because psi is a 1-1 map, so you can if there is a equality over here, there will be equality over here. So so this is what we have now. So 3 and 4 together give that psi x is less than equal to psi z is strictly less than psi y, implies x is less than equal to z is less than y. And in view of 2 says that whenever x is less than equal to z is less than y, this would always imply x is equal to z, because x is covered by y. So whenever x is covered by y, then if there is any z in between, lying between x and y, then that z has to be equal to x. So x is equal to z, and so from here, using 2, we have x is equal to z in view of 2. So basically this again, then this implies psi x, because x is equal to z. So psi x is equal to psi z, because psi is a function. So whenever elements are equal, the images are also equal, but the value of psi z is z1. So this means that this z1, which was lying from here, we can see from 3, z1 was an element in Q here, and it was lying between psi x and psi y. Psi x is less than equal to z1 is less than psi y. We had taken z1 to be like that. This is what we had started with, this particular line, and what we have got in the end after starting with line which has been marked in 3. What we have got is, we have got that psi x this psi x comes out to be equal to z1. So we started with this line, which was in 3, that is z1 was an element belonging to Q, such that psi x such that z1 lies between psi x and psi y, and this implies that this z1 becomes equal to psi x, which means that there cannot be, in other words, what does that mean? If there is any element z1, if we take z1 to be any element lying between psi x and psi y, then that z1 comes out to be equal to psi x. In other words, what does that mean? In other words, it means there does not exist any z1 belonging to Q such that psi x is less than z1 is less than psi y. There does not exist any element between psi x and psi y, because if there is an element between psi x and psi y, then that particular element z1 would become equal to psi x. So there is no element, a distinct element between psi x and psi y, and already psi x was strictly less than psi y. This we had seen over here. Psi x is strictly less than psi y. This is over here. So psi x is already less than psi y. So what are the two things that we are getting about psi x and psi y? Psi x is strictly related to psi y, and also there does not exist any element of Q between psi x and psi y, which means that psi x is covered by psi y. This is the definition of covering relation. So psi x is covered by psi y. So uh, we actually have got this particular conclusion that psi x is covered by psi y in Q. And what is that you started with in the beginning? In the beginning, you started with this fact: suppose x is covered by y in P. So if x is covered by y in P, we have got that their images also behave in the same way. That is, psi x is covered by psi y in Q. So this means that this is the line that we have, that if x is covered by y in P, then their images also behave in the same way, which means that psi x is covered by psi y in Q. So I'm marking this as star. This is one conclusion that we get. Now we have to prove the result the other way around also, which means that if the images behave in same way, which means that if psi x is covered by psi y in Q, if this is given to you, then you have to show that the elements also behave in the same way, which means that you have to show that x is covered by y in P. So the other way around also this has to be shown. So this is one part of the one sub part of the second part that we were trying to show. So now let me prove the converse of this whole thing. So the only thing that you have to right now remember is that this is the important result, important fact, important midway result that we have obtained, that if x is covered by y in P, then psi x is covered by psi y in Q. Now so now coming to the converse part. Now in the converse part, we just have to show that whenever the images psi x and psi y behave like this, which means that whenever psi x is covered by psi y in Q, then this also holds, which means that the elements behave in the same way, which means that x is covered by y in P. So this is what we have to show. So conversely, let psi x and psi y be such that psi x is covered by psi y in Q, then we have to show that x is covered by y in P. Now, by definition of covering relation, which I have already recalled, because psi x is covered by psi y in Q, so two things will happen. The first thing is that psi x will be related to psi y and strictly related to psi y, which means psi x will be related to psi y, but psi x and psi y will be distinct. This is one thing. And the second thing is that you cannot have anything in between psi x and psi y. Again, this is what we have to show, that x is covered by y. This is one thing. If you have to show that x is covered by y, what are the two things that you need to show? The two things that you need to show are firstly that x is strictly related to y, which means x is related to y, but x is not equal to y. This is one thing that we need to show. The other thing that we need to show is that there does not exist any element which is lying between x and y, which means there does not exist any z such that x is less than z is less than y. This should not happen. So if these two things happen, then you say that x is covered by y. If x is strictly related to y and if there does not exist any z lying between x and y, then you will say that x is covered by y. So my aim is showing this. Now, firstly, I have just, because I have assumed that psi x is covered by psi y, then the first fact that I have because of this covering relation is that psi x is strictly covered by psi x is strictly related to psi y. This is one thing that I have. So therefore, in view of one, now one says, because this is condition one, this one, because it was holding, this one was holding, because we are assuming condition two holds. So one is holding. One says that whenever the elements are strictly related, the images are strictly related, and whenever the images are strictly related in Q, then the elements are related in P. So this we are assuming to be true, because condition two is assumed to be true right now. So because you have that the images psi x and psi y are strictly related, so the elements are strictly related in P. So now, so this part has already been shown, that whenever the images are related, then the elements are related, strictly related. So this part has been shown. Now, in order to show that x is covered by y, I just need to show this, which means I need to show that does not exist any z lying between x and y. So suppose, just suppose the opposite. Let it possible, suppose, and we'll get a contradiction in the end. So let it possible, suppose there is a z which lies between x and y. So let it possible, suppose there is some z belonging to P such that x is less than z is less than y. We are marking this as 5. Now again, in view of one says that whenever the elements are related, then this implies their images are related, and whenever the images are related, then the strictly related, then the elements are strictly related. Now, because x is strictly less than z is less than y, then in view of 1, which is this, whenever the elements are related, then their images have to be related. So in view of 1 and 5, you have this, that psi x is strictly less than psi z is less than psi y. But then 6 is not possible. Why is 6 not possible? Because we just have assumed that psi x is covered by psi y, which means that psi, there cannot be anything in between psi x and psi y, and we have got psi z to be an element in between psi x and psi y. This is not possible. So this means that because this is not possible, so the assumption that we made in the beginning here, the assumption that we said that let if possible, suppose there is some z lying between x and y, this assumption is wrong, which means there does not exist any z in between x and y. So this assumption, because this assumption is wrong, so there does not exist any z belonging to P such that x is less than z is less than y, which means that this condition also holds. And because both of these conditions are holding, so which means that x is covered by y. So this implies that x is covered by y in P. So what we started with, let me just remove this mess altogether, so that we clearly have, it is clearly visible what we are starting with and what we are getting in the end. So what we started with here in the converse part was that this psi x is covered by psi y in Q. This is what we started with, and what we have got in the end is that x is covered by y in P. So whenever the images behave like this, that the image of x is covered by the image of y, then the elements also behave in the same way, which means that the element x will be covered by element y. So we have got this, that psi x is covered by psi y in Q implies x is covered by y in P. I'm marking this as star dash. So this is one thing that I had got, that if the elements if the elements are covered like this, then their images are covered like this. This we had marked as star. And now in star dash we have got that if the images are covered like this, then the elements are also covered like this, which means that if I take star and star dash together, we have both way implication is true. And both way implication we have is this, that if x is covered by y in P, then psi x will be covered by psi y in Q, and conversely also. So this is actually the case. Here, this is how the picture looks. P and Q are over here. If x is covered by y, which means that if you draw the hash diagram, x will be down and y will be up. So if x and y are behaving like this, that x is covered by y, then in the image set, the image of x, which is psi x, will also be covered by the image of y. So if x is at the bottom and y is at the top of x, then psi x will be at the bottom and psi y will be at the top of it. And this result is basically both the ways, which means if this happens, then this will happen, and if this happens, then this will happen. So this is what we have got, that x covered by y in P implies and is implied by psi x is covered by psi y in Q, and this is nothing but condition 3 which we were trying to prove. So condition 2 implies condition 3. This is the first subpart of the second part that we were trying to show. We were trying to show that this 2 implies and is implied by 3. This is what we were trying to show. Condition 2 implies and is implied by 3. And in this, what are the two things that you have to do? You have to show that if condition 2 is given, then condition 3 should be true. And the second part that you have to show is that if condition 3 is given, then condition 2 is true. So now this part we have already shown. This is the first sub part that I have shown, that if condition 2 is given to be true, then you have to show condition 3. This part we have already shown, and now I have to come to this part, which means that if condition 3 is given, you have to show condition 2 is true. And condition 3 is about covering relations, and condition 2 is about strict order relations. So let me move on to the second sub part of this second part of this result. So we have to show in this part that condition 2 implies condition 3 implies condition 2, which means that if condition 2 is given to you, condition 3 is given to you, then you have to show condition 2 is true. So let condition 3 hold. Condition 3 is about covering relations, which means if x is covered by y in P, then this implies and is implied by psi x is covered by psi y in Q. The images are also behaving in the same way, which means if elements behave like this, the images behave as covers, and if the images behave as covers, then the corresponding elements also behave as covers. This particular condition 3 I'm marking as 7, and now you have to show that condition 2 holds. And what was condition 2? Condition 2 was that if x is strictly related to y in P, then this should imply that their images should also behave in the same way, which means that psi x should be strictly related to psi y in Q. And if this happens, then the elements are also strictly related. So if and only if we have to show. So let me prove. So there are actually two parts to this particular subpart. First of all, you have to show that if the elements are strictly related, then their images are strictly related. This is one part you have to show. And the second part that you have to show is that if the images are strictly related, then the elements should be strictly related. So there are two parts that you have to prove in this particular part. So let me firstly prove this particular part, that if the elements x and y are strictly related in P, I have to show that psi x is strictly related to psi y in Q. So let me suppose firstly that x is strictly related to y in P. So let x be strictly related to y in P. What you have to show is that psi x is strictly related to psi y in Q. This is what you have to show. Now, as x is strictly related to y in P, because x is strictly related to y in P, there is a finite sequence of covering relations between x and y, which is like this. X I am denoting by x naught. This is just a notation. There is a finite sequence of covering relations between x and y. Y again I am just denoting by xn, just as a just to fall in line with the notations that we are taking. There is a sequence of covering relations between x and y, which means that x which we are taking as x naught will be covered by x1, and x1 will be covered by x2, and x2 will be covered by x3, and so on. Finally, xn minus 1 will be covered by xn, and xn is nothing but y. So actually this is a result that we have in a finite PO set, because all these are elements of P, where you have actually two PO sets which are given to you in the theorem. P and Q are two sets, and P and Q are both PO sets, and they are finite, and there is a mapping psi which is bijection from P to Q. This is already given to you in the result. So right now I'm concentrating on the set P, which is a finite PO set, and now we have x and y are elements over here. So there is a result which says that if x and y are elements are of a finite PO set P, then and if x and y are strictly related like this, if x is strictly related to y, which means that if you draw the hash diagram, x will be here and y will be here, will be at the top of x. Then the result says that if these elements x and y are in a finite PO set, then you can always find a finite sequence of covering relations between x and y. So here because there is a because x and y are related, so in the hash diagram x will be at the bottom. This line should actually be a straight vertical line. So let me make it a straight vertical line. So if you draw the hash diagram of the PO set, finite PO set P, as far as x and y will be concerned, this is a straight line actually. So if x and y are concerned, x will be at the bottom and y will be at the top. Now because x and y are in the finite PO set, so the result says that if x is strictly related to y, you can always find a sequence of covering relations between x and y, which means that x will be covered by some, you can find some x1 such that x is covered by x1, then x1 is covered by x2, and then let's say x2 is covered by x3, and so on. This before y, let's say the element we are calling before y, which is covered by y, I'm calling it as xn minus 1. So just to fall in line with the notation. This one I'm calling as xn and this one I'm calling as x naught. So if you are in a finite PO set P, and if you pick up two elements x and y in P such that x is strictly related to y, we are not saying that x is covered by y, we are just saying that x is strictly related to y. So if x is strictly related to y, then if you draw the Hasse diagram, then in the Hasse diagram x will be at the bottom, y will be at the top. This is how they look if x is strictly related to y. Then the result says you can always find some finite sequence of covering relations such that between x and y, such that x will be covered by some element x1, and x1 will be covered by some x2, x2 will be covered by some x3, and and so on, going on like that. Xn minus 1 will be covered by the element y. So y again we are denoting by xn, and x we are denoting by x naught. So, and if, of course, if x is covered by y, here x is strictly related to by y, but if x is covered by y, so the next element after x in the Hasse diagram would be y itself. So this is another thing, but here x is given to be strictly less than y. So using this particular result, we have that because x is strictly less than y, we are just using this result without proof over here, which is true for finite PO sets. So using this particular result, we have that because x is strictly less than y in P, so there exists a finite sequence of covering relations in P such that, or there exists elements such that x is equal to x naught, where x is, which we are denoting x by x naught is covered by x1, is covered by x2, and so on. Xn minus 1 is covered by xn, which is actually y. We are marking this as 8. So now taking 7 and 8 together, in view of 7 and 8, whenever the 7 says that whenever the elements behave like covers, then their images behave like covers, and if the images behave like covers, then the elements behave like covers. So in view of 7, what do you get from 8 is, because the elements are behaving like covers, so the images will also behave like covers, which means that psi x, which is actually psi x naught, is covered by psi x1, is covered by psi x2, and so on. You will have psi xn minus 1, which will be covered by psi xn, and psi xn is nothing but psi y. So in any case, this is what we have. Psi x will be covered. There will be a sequence of covering relations between psi x and psi y, and this finally implies that psi x is less than psi y in Q. Again, this is what we actually this particular result is if and only if this result is if and only if, that if x is less than y in P, then this implies and is implied by that there exists a finite sequence of covering relations in P like this. So if the elements are strictly related, then you in a finite PO set, then there will be a finite sequence of covering relations, and if there is a finite sequence of covering relations, then the elements will be strictly related. This result is if and only if. So so this particular line which we get, this is a finite sequence of covering relations that we are getting between psi x and psi y. So if you are getting a finite sequence of covering relations between psi x and psi y, so automatically, because the converse of this result holds, converse of this one holds, so from here you get this. If this is given to you, if finite sequence is given to you, you get that the elements are strictly related. So here you get, because there is a finite sequence of covering relations between psi x and psi y, so psi x is strictly less than psi y in Q. So this is one way of giving the argument. The other way of giving the argument is by transitivity in Q, because all these are covering relations, because psi x is covered by psi x1, so definitely psi x is strictly less than psi x1, and psi x1 is again covered by psi x2, so psi x1 is strictly less than psi x2, and so on. This is strictly less than psi x minus 1, and this is strictly less than psi y. And by transitivity, if the first is strictly related to the second and the second is related to the third, then the first is strictly related to the third one. So moving on like this, by transitivity, you have that this particular first first element, psi x, because of transitivity, this particular element will be strictly related to psi y. So you can use transitivity in Q because Q is a pure set. So you can use transitivity, or as I said, that this result is if and only if, that if the elements are strictly related, there will be a finite sequence of covering relations, and if there is a finite sequence of covering relations, then the elements are strictly related. This result is both the ways true for finite pure sets. So you can use this result also. In any case, this is what we have, that psi x is strictly less than psi y in Q. So we started with the x is less than y in P, and here we started with x, this here x is less than y in P, and we have got that psi x is strictly less than psi y in Q. So we started with this and we have got this. This we are marking as star double dash. So this is something we will use later on. Now let me prove the converse part, which means that I am going to assume that the images are strictly related, and I will show that the elements are also strictly related in P. So converse part I am going to prove now. So let me take the images to be in such a way that psi x is less than psi y in Q. Now what we have to show is that x is less than y in P. So as psi x is strictly less than psi y in Q, so using the result which we have just used, because the psi x is less than psi y in Q and Q is a finite PO set. So in finite PO set, I just said this particular result holds that whenever these are elements of psi x and psi y are elements of Q. So this is the image, this is the picture that you have. P and Q are over here, x and y are over here, psi x and psi y are over here. So psi x and psi y are elements of Q, and Q is given to be a finite PO set. And in a finite PO set, whenever two elements are strictly related, then there always exists a finite sequence of covering relations between them. Now because psi x and psi y are strictly related, psi x is strictly related to psi y like this. So in the Hasse diagram, psi x will be at the bottom, psi y will be at the top, and the result says you can always find a finite sequence of covering relations between them. So you can find a finite sequence of covering relations in Q, that is you can find elements W1 and W2 and so on till Wn minus 1, such that they behave like this. And just to fall in line with the notation, psi x I'm denoting by W naught, and psi y I'm denoting by Wn. So if you denote this by W naught, and if you denote let me just clear this off. If you denote this psi y by Wn, so you can find a sequence of covering relations in between W naught and Wn, because Q is a finite PO set. So you can find out W1, W2, and so on. The second last element will be Wn minus 1, and the last element is Wn. So all these Wi's, W naught, W1, W2, Wn, and Wn minus 1, Wn, all these are elements of Q. So this is just by using this particular result which we had used just before this. So, so you have that there exists a finite sequence of covering relations in Q's, that is there exists elements psi x is equal to W naught, this is just a notation, is covered by W1, is covered by W2, and so on till this is covered by Wn minus 1, and this is covered by Wn, which is nothing but psi y. We are denoting it like this. So now as W1, W2, and so on till Wn minus 1, they all belong to Q, and psi mapping from P to Q is an onto map, because these are all elements, these W naught, W1, and so on till Wn minus 1 and Wn, all these are elements of Q. We have something like this. As I said that we have two PO sets, P and Q, and you have W naught, W1, and so on till Wn. All these are elements over here, and as far as the map psi is concerned, psi is an onto map. Psi is a map from P to Q, but it is onto, which means that you should be able to find elements over here whose images are W naught, W1, and so on till Wn, because psi is an onto map. So as W1, W2, and so on till Wn minus 1 belong to Q, and psi mapping from P to Q is onto, so that you should be able to find x1, x2, and so on till xn minus 1 in P, such that psi x1 is equal to W1, psi x2, psi x1 is equal to psi x naught, x naught is actually x only, psi x naught is equal to W naught, psi x1 is equal to W1, and so on till psi xn is equal to wn. So psi x1 is equal to w1, psi x2 is equal to w2, psi xn minus 1 is equal to wn minus 1, and in fact psi x naught is actually psi x only, because we had just taken this as our notation, and this is w naught. And as far as psi xn is concerned, psi xn is actually psi y, and this is nothing but wn. So this is because psi is an onto map. So this we have marked as, this particular result we have marked as 9, this one we have marked as 10. So now using the values of these wi's from 10 in 9, so I'm putting the values of wi's from 10 in 9. So this is what we have. So using 10 and 9, this is the set of, this is the sequence of covering relations that we have. Now in view, and this we are marking as 11. Now in view of 7, 7 says that whenever the elements behave like covers, then their images behave like covers, and whenever the images behave like covers in Q, then the elements behave like covers. This result is if and only if. This result is implies and is implied by. So now here the images are behaving like covers, and so the images are behaving like covers, and here this means that this automatically implies that the elements are behaving like covers. And from here again you can just, in this whole thing just simply implies that x is strictly less than y, because you can either use transitivity, and because these are covering relations, so because x naught is covered by x1, so x naught is less than x1, because x1 is covered by x2, so x1 is covered by x2, x1 is less than x2, because x2 is covered by x3, so x2 is less than x3, and so on. We have xn minus 1 is less than xn is equal to y. So and so because covers are in any case strictly related elements, and so because the first is strictly related to the second and second is strictly related to the third, so by transitivity first is related to the third strictly, and continuing like this, you will finally have that the first element, which is this one x naught, will be strictly related to xn, which is equal to y. So this, here you can use transitivity also. This is one way of giving the argument, so this is one way which I just said, that you have to use transitivity in P. These are elements of P, not Q. So either you can use transitivity and you can conclude this particular line from the above line, or as I said, that because P is given to be a finite PO set, and in a finite PO set, whenever you have a finite sequence of covering relations like this, whenever there is a finite sequence of covering relations like this, xn is equal to y, then this implies that x is strictly less than y, and if x is strictly less than y, then there exists a finite sequence of covering relations. So in a finite PO set, this is always true. If there is a finite sequence, then the elements are strictly related. If the elements are strictly related, then there is a finite sequence of covering relations. So you can use this particular result also, which I have used earlier, this one, this result, but here these are elements of Q, but here these are elements of P. So you can use this particular result, or you can use transitivity in P. These are elements of P, although transitivity holds in Q also, but right now we are using transitivity in P because these are elements of P. So you have to write P over here, not Q. So so finally this is what you have, that this is what we started with, that psi x is strictly less than psi y. Here this is what we started with, this particular relation, that psi x is strictly less than psi y in Q, and what we have shown is that x is strictly less than y in P. So from here we have reached this point. So this is what we get in the end, that psi x is less than psi y in P implies x is less than y in psi x is less than psi y in Q implies x is less than y in P. This we have marked as star triple dash, and now using star double dash and star triple dash, this is star double dash, x less than y implies psi x less than psi y, and star triple dash is the opposite. So combining star double dash and star triple dash, combining these two, we get the result is if and only if, and this result basically which we have got now, this is nothing but condition 2. So we started with condition 3, we assumed condition 3 to be true, and we have got condition 2, which means that we have shown that condition 3 implies condition 2. This is what we have shown, and already we had shown that condition 2 implies condition 3. This we had already shown. So both the things we have shown now. So this means that we have proved that condition 2 and condition 3 imply each other, which means that condition 2 and condition 3 are equivalent. So this part we have just shown that condition 2 and condition 3 are equivalent. As far as this part is concerned, this was the first part of equivalent conditions related to order isomorphism for finite PO sets. This was proved in the first video. So if you combine the two results together and if you write the whole proof together as one, then we get the proof of result 2, which means that conditions 1, condition 2 and condition 3, all three are equivalent, which means if one condition is given, then the other two will definitely hold. If any one of them is given, the other two will automatically hold. So this is the proof of result 2, which is an important result relating to finite PO sets, and if there is a bijection which is given in between them. So this is an important result which gives equivalent conditions related to order isomorphism for finite PO sets. So that is all about in result 2.